Okay, please correct. There is a number 84 here instead of 8. I made a mistake. In the very last equation that we have written, there is 4 instead of 8. The reason of the mistake is that I was thinking in terms of peak amplitudes and not RMS. Okay, so my mistake. Okay. Now let's find eventually the relation between the effective area and the effective length of the antenna. As I said, those are two electromagnetic parameters, not geometrical parameters. Okay, so what we have. I'm rewriting this by replacing voltage with this product. So please remember that we found another definition of the received power, that is the incident power density times the effective area. That is this expression comes on the and since you remember that this is real, so this is That's where it comes from. So those two must be equal, obviously. We are talking about the same thing. So if we put we find out that those things cancel and the effective area is equal to the effective length squared, but in a quite complex way. So yes, the area is related to the square of the length, but there is also the impedance and the free space impedance. But this is useful when we have to calculate the effective area if we know the effective length and vice versa. There is another equation that we will use when the time comes. Now, I will not have many other information on the antennas at this time. I will just add the last piece of information, that is if the electromagnetic wave is coming from a direction that is not the best direction for the antenna, so coming from a generic direction, you take this into account by introducing the antenna directivity function. So the generic direction is identified by the coordinates, the angular coordinates theta and phi. This is the direction with respect to the antenna. The antenna is, and the wave is coming along this direction, and you just multiply everything with the antenna directivity function. So at this point we have all the pieces that we need to derive the link budget. And that's what we will do now. Questions so far? We'll now work out the link budget in free space. And then I will show you some antenna directivity functions that are typical for those applications. Okay, so the link budget means we have a transmitting antenna. And the generator is injecting a power P into the transmitting antenna. And let's assume that the direction of maximum radiation is not necessarily in the direction of the receiving antenna. Then we have the receiving antenna. Again, the direction of maximum sensitivity of this antenna is not necessarily in the direction of the transmitting antenna. And then we have the distance R between the two antennas. We want to calculate what is the receiving power at the receiver end. So we know that the receiving power, we have seen that before, is the power that is incident, power density that is incident on this antenna here, multiplied by the effective area of the receiver, because the two antennas can be different. They are not necessarily the same kind of antenna. So the effective area of the receiver times the antenna directivity function, I will try to write bigger, so, of the receiver. But the power that is incident on the receiver depends only on the transmitter and is equal to the power that the generator is injecting into the antenna times the gain of the transmitting antenna times the directivity function of the transmitting antenna, that can be different, divided R squared. So if we put this expression into the previous equation, what we got? Transmitted power times the effective area, but I will use, instead of the effective area, I will use the universal expression and replace the effective area with the gain of the receiving antenna. The gain of the receiving antenna times the directivity function of the receiving antenna. I can put everything together here, and this is going to be lambda divided. That is our link function. This equation is also called Freeze equation. And tells you what is the power that you receive if you know the power that you transmit and all the other parameters. Now, usually this equation is represented in a block diagram like this. You have one block that includes these terms. That is a block that includes all the parameters of the transmitter. Then there is this block. And this is what is called free space loss, or free space isolation. And this is a number that is much, much smaller than 1. And it mainly describes the geometrical losses due to the distance between the transmitter and the receiver. Okay, why do we write things like that? Well, first of all, because you identify which parameters are relevant to the transmitter and to the receiver. Depending on the application, you may have control on the transmitter or the receiver or both. So how you balance all the components in this equation depends on what kind of control you have of your system. And also more important, because this quantity here is called FIEC. That is an acronym that stands for equivalent isotropically radiated power. The dimension of this number is watt, obviously. Why it is important? What is this, first of all? Well, as the name says, is the power that you should radiate with an isotropic antenna to have the same power at the receiver. It is important because the government or the lawmakers or whatever who decides the radio regulation, the International Telecomunication Union or whoever, when they fix the limits for certain applications, they set the limits in terms of air, not in terms of transmitted power. For example, I don't know in this part of in your country, but in Italy, for example, in Wi-Fi, if you have a Wi-Fi access point, by law, the air must be less or equal to 100 milliwatt. Maybe also in this country, there can be some variation, but not much like that. It means that the product of the transmitted power times the gain must be less or equal to 100 milliwatt. It means that you cannot cheat. You cannot replace the antenna with an antenna that is got a higher gain. If you do this, you have to reduce the power of the transmitter. Otherwise, you are violating the law. And the basic concept behind this is that whatever combination you choose between power and gain of the antenna, if this is the limit, you will always have the same power as the receiver. That is, the coverage range of your Wi-Fi access point will always be the same. Okay. So when you look at the regulation, they are always given in terms of area. Equivalent isotropical relativity. So how do you choose those two parameters so that their product gives a given value of A? Usually you choose for the lowest cost, whichever combination between transmitter power and antenna gain is less expensive. Unless you have some specification on the directivity function and then the gain is given. Okay, we will do some exercises on this later on during this course. Okay, questions? Okay, now usually when you design a radio link, you choose or point the antennas so that the directivity functions are maximum. You point the antenna in the direction of maximum radiation. So if the antenna are, I would say, well pointed to each other, then for that particular direction, the antenna directivity function will be equal to 1. So you can rewrite that equation like this. I just put this is equal to 1 and that other one is equal to 1, so and since this ratio is a huge number, because the received power is many order of magnitude smaller, usually smaller than the transmitted power, it's easier to express everything in dB on a logarithmical scale. If this is the case, we got what I call that, what the number there is the insertion loss. And we call it LF. That is the insertion loss. Please remember that when you calculate the logarithm of A times B is equal to log A plus log B. So all those products become a summation. That's also one of the advantages of the logarithmic scale. So you got of the gain of the transmitter antenna plus now please also remember that power b is equal to b times logarithm of a. So this exponent there comes here, and you have then 20 logarithm. Now this is the antenna gain in dBi. This is the receiver antenna gain in dBi. That is something you easily find on the specification. And then you can change things a little bit by remembering that lambda is equal to speed of light divided by the frequency. So at the end, with a couple of manipulation, you'll find out that the insertion loss is and then you can express everything in function of frequency. You find minus 20 of the frequency minus of the distance plus a constant k is 7.6. Okay, this is just a more convenient expression of the link budget, but it's perfectly equivalent to this one. So, what we can assume from this equation? Okay, every time the distance doubles, so we go from 1 to 2 meters, from 2 to 4, from 4 to 8, every time the distance doubles, the power is reduced by 6 dB. We lose 6 dB every time the distance doubles, or 20 dB for every decade. That is, every time the distance is multiplied by a factor of 10. This kind of information is useful when you have to dimension a link and you say, okay, if my distance increases by a factor of 2, you know in your head that you lose in free space 6 dB. So you can easily work out the link budget in terms of dB. Okay, and there is not much more to say about free space because nothing happens in free space. We will see that in our real world things will be very different. And we'll start looking now at the effect of the graph as the first thing. And we shall see that things can be very different from free space. Before we move to the ground, I will show you some antenna directivity function just to hopefully can be easily seen. But there are questions before that?
Cuando ves eso explica, se dobla, se reduce. ¿Cuánto es tu pagar esa? Antes de cuánto tengo.
Yes. If you look here, you can look my local time. 2:50 in the morning. 10 minutes to 3 o'clock in the morning. Okay. What we will see here, this is the horizontal plane, so the way that the antenna radiates on the horizontal plane. The vertical plane is usually less important, because you don't have much users on the vertical plane. Usually your users are all around you. So this is the omnidirectional antenna. You cannot see much because the radiation diagram is constant along the circle. The antennas are never exactly omnidirectional. That is, there is expect a little bit of fluctuation in the transmitted power, but usually it is acceptable 0.5 dB of fluctuation of the transmitted power. So if it is more, you can complain. If it is less, you cannot complain with the producer. This number here, there is no legend, but this is the maximum gain in dBi that you can achieve reasonably. So you cannot ask for an omnidirectional antenna and say 20 dB of gain, unless you do something that is very special, but it's usually not the case. Okay, so this is a semi-omni antenna. That is, the radiation diagram is this line here. So it is radiating in this direction. There is very few radiation in the backward direction. And it's called semi-omni because it covers a radiation angle on the horizontal plane between 120 and 180 degrees. It's ideal, for example, if you have to cover a corridor or this room. You put an antenna on the wall. There is no reason to have an omnidirectional antenna that radiates also towards the wall. So if you have to cover this room or a corridor, you choose kind of a semi-omni antenna. Again, the gain is not brilliant because those radiation diagrams are still very wide, very large. Okay, now you get narrower radiation diagram, 90 degrees. It's called sectorial antenna, and you can do you can have 7.5 dB of gain. This is again a sectorial antenna that is narrow, 55 to 65 degrees of radiation angle, 10 dB of gain. Okay, let me show you how the antennas actually radiate. I'll show you some simulations just to okay. This is an electromagnetic simulation software. So the simplest antenna that you can build, it's a dipole. It's a simple straight wire, like the one that you have on your cars, for example, the one that you have on your access points, this kind of thing. This antenna radiates this antenna radiates in all directions. Let me put this over here. So this is the radiation diagram of the antenna. The warmer the colors, the stronger the radiation. You can see we have a gain of 2 dBi. That is not much. But this is an antenna that is pretty omnidirectional. This is the way it radiates on the vertical plane, and that's the way it radiates on the horizontal plane. Horizontal plane, vertical plane. So it's omnidirectional on the horizontal, but not on the vertical, obviously. If you want to concentrate the antenna, the radiation in a given direction, you use more complex antennas. And I will show you some examples. If you use 2 antennas instead of 1, 2 antennas instead of 1, you have a radiation diagram that starts to get narrower. This antenna is radiating more in this direction and this direction. And you see that the gain is up to 6 dB. There was a question yesterday about tilting the radiation diagram. If you change the phase between the 2 antennas, you can make this thing radiate in other directions. You keep on building and you put more antennas on the scene, so you put more complex systems. Those are 3 antennas, and those things concentrate even more the radiation pattern. They radiate, the gain is 7 dB, it radiates in 2 directions. They're easily visible here. This is the radiation. This is the 3-dimensional radiation diagram. This is the 3-dimensional directivity function that we talked about. Or if you want to make it radiate only on one side, you can put a screen. I just show you one antenna that is highly directive, and then we move on. This is no, this is not what I was looking for. Sorry about that. I was looking for something more complex. Okay. This is an antenna with 6 elements and a screen behind. And if you look how this antenna radiates, yeah, the radiation is really concentrated in one direction, in the frontal direction. The gain is very high, 13 dB. 13 dB means 20 times. 20 times means that if you compare in the direction of maximum radiation this antenna and an isotropic antenna fed with the same power, the field, the power density generated by this antenna will be 20 times higher, and this is the gain, 20 times stronger than the density power generated by the isotropic antenna. But you are gaining in this direction and you are losing in all other directions. And you can see by comparing this with the dipole that was radiating the same power all over the place. So there are no free lunches. So the idea is, first you decide what is the radiation pattern that fits your application, and only afterwards you calculate the gain, and what you get is what you get. Okay? Questions? Okay. Oops. Okay. So good for the antenna directivity function. Let's go back to one of our research areas is designing antennas, but this is not a topic of interest for this course. Okay. Let's move from free space to our planet. Okay. What is the effect of the ground? The effect of the ground is to generate a reflected electromagnetic wave. So let's suppose that we have our transmitter here. There is an electromagnetic wave. An electromagnetic ray hits the ground in a given point. We know that what happens, a reflected electromagnetic ray is generated. And we have two different situations depending on the polarization of the incident wave. And we will discuss this in a moment. Now, first of all, the properties of the ground. As I said, with ground I mean also water, salt water, fresh water, anything that is a flat horizontal surface. The properties of the ground are described by the conductivity, failing, and dielectric constant. And those two parameters are highly variable depending on the kind of ground that you are dealing with. Now, the situation is different when you have the so-called vertical polarization. There's the electric field, the direction of the electric field of the incident wave. The magnetic field will be obviously perpendicular will be perpendicular to the electric field and perpendicular to the direction of propagation. So the magnetic field, you can imagine, is perpendicular to the black hole. Like this. We usually neglect the magnetic field. So this is electric field of the incident wave. And then we have the electric field and magnetic field of the reflected wave. So this is the incident wave, and this is the reflected. It can be demonstrated by the usual, and it's the so-called Snell's law, that the two angles, the angle of incidence and the angle of reflections, are the same. We could not demonstrate it. But at least the angles are the same, so the geometry is simple. What is the amplitude of the reflected wave? How strong it is? It depends on the nature of the ground. And the incident and reflected wave are related to a coefficient that is called the reflection coefficient of the ground. And again, can be a complex number. Usually it is a complex number. Okay, this kind of situation is called vertical polarization. You may say, well, but the electric field is not vertical with respect to the ground. And in fact, vertical polarization is not strictly correct, but is the orthogonal polarization with respect to the horizontal polarization, where the electric field is effectively horizontal with respect to the ground. So the electric field is not vertical, but this is called vertical polarization. Please note that the reflection coefficient, the absolute value of the reflection coefficient, must be equal or minor or equal to 1. In other words, it is not possible that the reflected wave is stronger than the incident wave. Otherwise, it would be carrying more power than the incident, and this is not feasible. I tell you because maybe we have to do some calculations, and we all make mistakes in calculations. But since you are engineers, some mistakes are not permitted. That is, if you have an exercise where you have to calculate the weight of a man, and you get 10 kilos, 100 kilos, or 1 ton, you must be able to say which of those solutions is realistic and which is not. So, if you do your calculations and you get a reflection coefficient that is greater than 1, this is clearly wrong. Cannot be like that. So this kind of errors are not conceivable for an engineer. Okay. Okay, now we don't go into the mathematics of this. I give you just the equation that may be useful to do calculations. Okay, now let's call for this polarization rho v. No, let's put it here. Where is this place? Reflection coefficient for vertical polarization. It can be demonstrated but the demonstration is very boring. That this coefficient is as follows: minus jx. I will tell you what x is in a moment. I don't remember this by memory. This is just an equation that can be useful if you have to calculate the reflection coefficient of whatever.